cells, you have to isolate only that. You cannot have the presence of other cells because that is going to interfere. Okay, it's going to load up to any cells that you're doing because it's a lipophilic compound and it will go across the membrane which is lipophilic. So, and that's the reason why when you are labeling with indiamoxine or HMPIO, they are lipid soluble compounds and they will go across the membrane because the membrane is lipid. So that's the mechanism that is used. But now I'm going to demonstrate it's a different compound called the tin colloid. Okay, a colloid is what? You have seen suspensions and colloids. You know, colloid means something which has got a particle size. If you put DTPA into a solution, you know, it dissolves completely, or a salt, sodium chloride into water, it dissolves completely. It's a solution has got a no charge, no size. But in here, you're looking at a colloid which has got a size. The reason for that, when you make a size, a colloid of a definite size, you know, the phagocytic cells, like the white cells, or the polymorph or nuclear leukocytes, you know, they take it up and then engulf it, you know. So that is called phagocytosis. So because a colloid is taken up only by the phagocytic cells, there is no need for you to separate platelets or the red cells from the solution. So you can use the whole blood as such. So it is a convenience over the other methodology. The only limitation is you have to make a colloid which is predominantly between 1.2 and 2.1 micron in size. Okay? So a lot of chemistry in nuclear medicine we use using the size of the colloid. The smallest is thin colloid, which is 1.2 to 2.1 micron, and then much bigger than that is lymph colloid, which has got 10 micron diameter, and then you have sulfur colloids, phytate colloids and all that, and then the biggest we use is MAA, macro aggregated albumin, which has got between 30 and 90 or 30 and 100 microns. So depending on the size of the colloid, the distribution varies. A small one like this will be taken up by the leukocytes, so we are planning to make that. So now I'm going to demonstrate how it is done. So I'm having two vials in my hand, vial A and vial B. Okay? Vial A has got sodium fluoride and vial B has got stannous fluoride. Okay? So the early worker, what he has done, they put the formulation both together into a solution. And the mistake in that one, the moment you are mixing a metal like tin into a fluoride medium, what you are going to get is the growth of the particle. So you want to control the growth, so you can control the size. The longer you leave it, the particle size becomes bigger, and then the two particles will join together and clumping, bigger size, non-uniform. You don't want all this mess. What you want is a straight technology, fully controlled. So the later work defined in 1986, Ross Hanna et al. From Australia, they developed two vials. One is sodium fluoride, a separate solution, and stannous fluoride, a separate solution. You're ready to go ahead, then you mix the two together. So the step one, I'm going to transfer some solution from A into B. And that will give you a fluoride medium for a metal ion, and that is a signal for it to go and grow as a particle. And by controlling it for 1 hour, I can make a particle size predominantly. More than 85% of the particles we are getting is going to be in the size between 1.2 and 2.1 micron. And the white cells love it. They eat them like durians. They love it because, that's what I want to do, calculate, go much. So what I'm going to do, prepare this one, And preparing a colloid itself is no good. I need to have it tagged with a technetium. How do you tag it with a technetium? Just mix the two together. I'm not greedy, I'm not going to take the whole lot of the solution. What I need is between 1 and 2 mils of the solution. And then I'm going to add this 1 or 2 mils of the solution into a syringe which has the technetium. And then you have the colloid, you have the radioactivity, so the two together will give you a technetium labeled tin colloid. And this process, after mixing, I'm going to rotate it for 1 hour. So by controlled mixing on a rotator, 1 hour later, you get a particle size, a minimum of 1.2, maximum of 2.1. I'm saying this particle size more and more often so that you'll remember this one. And that is the preferred size for white cells. And the other thing I'm going to do, this colloid, once it is made, there is no sort of a hard and fast rule that you have to use it within an hour. You make it, you can use it between 1 and 4 hours. So in practice, we recommend between 1 and 2 hours after the preparation, you can comfortably use it. So if you have more than one patient, you want to handle it, you can use the same solution for up to 2 hours after the preparation. So don't be scared of using it because the particle does not grow once you stop rotating this one. And there will be some growth, but it doesn't matter. So the more than 85% of the particle size will be in the desirable range of 1.2 to 2.1, and that is going to be taken by the white cells. So when I make the colloid, which is technetium labeled, and then put it to blood, which contains red cells, white cells, platelets, and you name it, all sort of cells. But only the phagocytic property you have only for the leukocytes or the white cells. So the white cells will take it up preferably or preferentially, and then all the colloids will be taken up by the white cells. But nothing is 100% in life. So some fraction of that will be taken by the red cells as well, because you have the tin, you have the technetium, so the red cells also will be taking it up. So when you inject it back to the patient, you will see there is a bit of activity in the liver. And that is partly because the red cells labeled with technetium, and also a certain amount of the white cells are going to be taken up by the liver as well. So there is a big donor is the liver. The second or the first biggest donor is the infection lesion, which has got the bacteria. So these white cells, which has got the capacity to go and accumulate at the site of infection, so that will take care of the process of accumulation of white cells at the lesion where you have the infection, and that process called chemotaxis. Okay, so when there is an infection, it sends the chemical signals, and in response to the chemical signals, the white cells go and accumulate at a place where there is a bacterial infection. So that is the mechanism, and that's what is happening. You are labeling the white cells, which is tagged with the technetium, and the reason why it is going to be staying inside the white cells because it is phagocytosed and internalized. So they are locked in the white cells, and then the white cells get the signal or the chemotactic signals, and then they go into the infection site, and then you can visualize that once you are putting the patient under the gamma camera. If there is a big infection in the joint, you can see that one has an infection lesion. Or it could be a cellulitis, bacterial infection, or osteomyelitis, bone infection. It doesn't matter. Or an abscess, or Crohn's disease, or your IBD, inflammatory bowel disease. All these diseases, they have an underlying mechanism of infection and sometimes complicated with inflammation as well. So that's the reason why this technology has been adapted, and we've been using it for the last 18 years. And it started with using this one in the adults, and then because of the convenience of only having 7 to 10 mils of the whole blood for this procedure, we started using in the pediatrics. In the children, it is the biggest problem. Many children are presented with IBD, inflammatory bowel disease, which is very, very common. We do about 2 patients per week on an average. So that's about 100 patients per year we do, Crohn's disease or the inflammatory bowel diseases, pancolitis or colitis and things like that, which is inflammation related to the intestines. So these infections, are fantastic. This has got a very high specificity, and that is the reason why we use that in pediatrics. Okay, so I'm not going to go into the lecture part of it too much because we focus on the practical side. Okay, the step 1 I take vial A.
Sorry, can you just say what's in vial A again?
It's sodium fluoride.
Sodium fluoride.
And this is vial B. I have stannous fluoride. I told you, any metal, put that in a fluoride medium, they grow. They grow into a particle. A particle has got a size, and that's what you're going to control and make and prepare. So I'm going to transfer 5 mils of solution, which is sodium fluoride, into a vial which is freeze-dried, containing tin fluoride. You know why it is freeze-dried? Tin does not like oxygen. You have a solution, put that into a tin solution. Oxygen dissolved in saline is going to oxidize your tin over the time. So you cannot afford to have this in a liquid form. It has to be freeze-dried, and that's the reason why you closely examine it. You can see water. Solution here, sodium fluoride, no problem. But here you have a tin. Tin has to be in a reduced form for binding the technician. So that's the reason why it is freeze-dried and evacuated or filled sometime with argon or a neutral gas, so that there is no oxygen, so there is no oxidation of tin. So this is preserved and protected. So when you put this one into this one, then the particle can be made from that one. Okay? So the first step, I take 5 mils from here and add it to vial B, which has the tin fluoride or stannous fluoride.
Tin fluoride.
ฮะ
Tin
ตี
fluoride.
นฟลูออไรด์
เรียกว่าคนลอย
สแตนนัท
แต่นะเขาเรียกฟลูออไรด์
ใช่
กับโซเดียมฟลูออไรด์